Hi. Hi, everyone. Good morning. Thank you for coming, all of you. So we have Irene, our colleague. We start with a nice presentation of our speaker today. And don't forget, there's a coffee break after.
Well, it's a real pleasure to have Gergö popping for the seminar this week with us. Gergö is one of those rare astronomers that has an expert hand in multiple things from theory to observation. So he did his PhD in theoretical astronomy in 2014 in University of Groningen, focusing particularly on semi-analytical models of galaxies. And his papers are about the evolution of cold gas content of galaxies are the ones that are very famous, and lots of references too. But then he joined ESO in Garching as a fellow, and that was when he was introduced to the observational side of the astronomy. So at that point he changes his focus on modeling dust in galaxies and using ALMA particularly. Then he joined MPIA, and there he was the theoretical lead for an ALMA large program aspects. And from there, in 2019, he rejoined ESO as a staff member within the ALMA Regional Center, where he coordinates all the ALMA user support, among others, within Europe. And scientifically, there's a lot of, we have a lot of collaborations. He focuses a lot on gas and dust evolution of galaxies throughout cosmic time. And in this new cycle of ALMA, we are co-leading a large ALMA program. And I'm sure you'll hear a little bit more about it to study dust and gas at high redshifts.
Okay, hi everyone. Can you hear me properly? Okay, thank you, Irene, for the very kind introduction. Indeed, I do everything, but it means I do everything a little bit, but nothing really a lot, right? I understood that today is the first time that you'll have coffee after this seminar, so I'm honored to be the inaugural coffee speaker. So it also means that if you know that there's something rewarding at the end. So please stay with me and enjoy it. Indeed, I work at ESA as a staff astronomer. And scientifically, I focus mostly on the gas and dust content of galaxies and how that evolves over time. And I'm going to start with a figure that you may or may not have seen already, but this figure provides a schematic overview of the history of our universe. Starting on the left-hand side with the Big Bang, the expansion of our universe, then you see the CMB. Then here we go. Oh, there it is. So you CMB, then we go through the dark ages, then the epoch of reionization. We're here at redshift 13 to 5.6 or so. This is an epoch where James Webb is now providing a lot of new contributions. But most important for this particular talk is then we're going through an epoch about here, which I can show better like this, which is called cosmic noon. And why is this epoch so important? Because at this time, cosmic noon, when the universe was about 3-4 billion years old, half the mass of stars that we see in our local universe today were formed at that time. It's the period in our universe where the period in time when our universe was most actively forming stars, and most of the stars were formed. Galaxies were really settling into the structures that we're starting to see today. And then it goes on to the present day, all the way here at the right. And this cosmic noon is usually shown in this way. What you're seeing here on this plot on the y-axis is the amount of star formation in our universe within some volume. And on the x-axis, you see redshift, or age of the universe, so to say. And you see this clear peak around a redshift of 2-3 when the universe was a few billion years old, when most of the stars were forming. And then it decreases again to our current day value on the left here. This pointer doesn't really work, but on the left here, which is today. And this, I mean, I'd like you to appreciate that even just this diagram essentially summarizes 20 years of work of studies of putting this together. Now, you'd say, great, then we know that this exists. And now what? well, then the next question is, why does the universe do this? Why do we have this peak in star formation at a redshift 2? So a way to look into this is to think, okay, how do you get stars? How are stars formed? So to form stars, you need gas, you need dense gas, you need molecular gas. And this is where ALMA started to play a really major role, because ALMA was the first instrument that allowed us to, together with NOEMA, that really allowed us to do blind surveys of the sky where you would just look and say, okay, how much gas is there at a given redshift? So you could make the equivalent of this previous plot, the star formation density. You could make a plot telling you how much molecular gas out of which stars can form is there at a given time within a volume. And then you see a very similar trend. It increases from the right-hand side, earlier times, up to a redshift of 1.5-ish to the same time where this peak in the star formation happened, and then it decreases again. Okay, so that's already a beautiful story, because it tells you from here to here, there's just more gas available there, and that allows you to form stars, to form more stars. Now, but we can zoom in a little bit further, because if you go back to these papers that really summarize all the work that was done in the late 90s, in the 2000s, in putting together the history of a universe, then there's also a plot showing you this, which is, again, the amount of star formation that there is in a universe, but traced in the infrared versus traced in the UV. Now, why is this important? The UV are the young stars that recently formed, and you see their emission directly. The infrared is actually the emission from these young stars that was absorbed by dust and then is re-emitted in the infrared. And what you immediately see here is that the amount of star formation traced through the infrared, which is actually this obscured star formation because there's dust in front of where the star formation is happening, the amount of obscured star formation is significantly higher than the amount of unobscured star formation. So that already tells us, okay, we know that there's a lot of gas. We also know that there's a lot of dust. So we should probably understand better what the dust in galaxies really is doing, how it is coupling to the gas, etc. And just to give you a graphical representation of this, what I'm showing you here is a spectral energy distribution of a galaxy. So how bright this is just an example galaxy, how much light it emits at given wavelengths. And on the left-hand side, you have the optical regime going down to the UV wavelengths. And on the far right-hand side, you have the infrared regime. And the blue line that you see here, it would be the spectrum of this galaxy if there were no dust at all. And the red line that you see is a fit to what we actually observe. And really what it shows you is that dust absorbs all that emission to go from the blue horizontal line downwards and then re-emits it in the infrared. So focusing on this infrared component is really important. That has been done, of course. Here again, ALMA played a major role. This is a plot that I took from a paper by Gergö Zavala, and what Gergö did was he carefully counted how many galaxies he was able to find with dust emission, and through a forward modeling approach, reconstruct over cosmic time what the fraction of obscured star formation is. So this is a plot very similar to the one you saw before, and then you see that essentially from redshift 3, when the universe was about 2 billion years old, to today, most of the star formation happens in obscured, dusty environments. Okay, so this is all great. We've learned quite a lot already, and I'm just glancing over this in an introduction, but this in itself is already essentially 10 years of ALMA science pushing things that were not possible before. Then the next thing you may want to ask yourself, okay, we have these galaxies, but what do they really look like? If we try to zoom in on them. And what I'm showing you here is a compilation of kind of the state-of-the-art zooming into galaxies, into their dusty or gas properties. First I'm going to tell you the highlight. The highlight is that this is even possible, that we are able to resolve galaxies, to resolve the molecular gas content of galaxies. These are just a few examples. And then you see nice smooth structures. But the fact that this is possible is great, because it's really only because we have sensitive submillimeter instruments these days. At the same time, if you look carefully, you see that we're not really resolving them properly. In every image, the beam is shown on the bottom left side, which is this black circle, or circle in a color. And you see that when I say here resolving, it's just we are resolving it in a couple of elements. So there's still a lot to learn about what the structure of these galaxies really is. And actually going back to this particular image, you would say, great, we looked at the sky for a long time and we counted how many CO emitters there were and where they are, and that way we were able to reconstruct how much molecular gas there is in the universe. This is all fantastic and really has been really challenging. But if you dive into these papers, then what you're seeing is that actually this is just based on a few tenths of secure detections. So it's really just the tip of the iceberg that we're probing here. And the same for this particular plot, or I said that what Gergö did was he was looking for galaxies that emitted continuum wavelength tracing dust emission. It's really just based on forward modeling of 13 objects in the particular field that he studied that were securely detected. So on the one hand, we've really made a great leap in the last decade in studying what gas and dust at redshifts at cosmic noon, when most of the stars in the universe were forming, but it's really just the tip of the iceberg. What I'm showing you here is what is typically called the main sequence of star-forming galaxies, and on the y-axis you have the star formation rate of galaxies, and on the x-axis you have their stellar mass. And as it turns out, is that most galaxies at a given cosmic time, most galaxies follow a beautiful trend in this particular diagram, which you could see as normal galaxies. Then the normalization of this changes a little bit with time. So in the earlier universe, for a fixed stellar mass, galaxies were forming their stars at a higher rate. But if your galaxy falls on these colored bands, it means that you're looking at a normal galaxy. But actually, the galaxies that I've talked about so far that are responsible for these plots, these 13 with high signal-to-noise ratios, the few tenths that went into quantifying how much molecular gas there is in the universe, some of them fall even above this trend, meaning that they're very actively star-forming, not a normal galaxy anymore. And they all lie very much at the right-hand side, only the most massive ones, really. To show that more properly, this is an image that I took from one of the papers from the ASPEX Large program. The ASPEX Large program has been one of the driving programs to create this plot of how much molecular hydrogen there is in our universe at a given time. On the x-axis, you see stellar mass, and on the y-axis, star formation rate. So the exact same as before. And then these colored lines show you kind of the trends at different redshifts that in the previous plot were shown with different colors as well. And what I want you to take away from this is, first of all, if you look at this orange shaded area, that's where most of our statistics about individual galaxies come from. They all lie in this top right corner, only the massive ones out there. Then the ASPEX survey was responsible for the individual data points that you see there. They go a little bit further down to stellar masses of 10 to the 10.5 solar masses, or even a little bit less. But if you look more carefully, the lower mass ones are actually all the nearby ones. And what I talked about earlier, cosmic noon, redshift 2-ish, when most of the stars in the universe were formed, that is not really probed at this low mass end at all. So really what we've done so far, it has been transformational in our understanding of what gas and dust is doing at these redshifts, but it's only the beginning of it. And what is missing is we're missing galaxies at lower masses at these redshifts. We're missing to actually properly resolve them, so we can actually see where the stars are forming, or where the dust is located, or where the gas is located. And often we're also just missing a full baryonic information. We might know how many stars they're forming or how massive they are, but then we don't know how much gas there is. Or if we do it, then we actually don't know how many metals there are or how much dust there is. And you need to put all of these together to build your full senses of what the baryons in galaxies are doing and how they are interacting with each other, and how physical processes like the star formation, supernovae that drive out winds, or active galactic nuclei, black holes that put a lot of energy into the ISM or heat up material. You need to know about all these baryonic components to really put that story together. So that drives me to, what are the properties of normal star-forming galaxies at cosmic noon? So not the tip of the iceberg, but the points that I mentioned before, going to lower masses, to galaxies that maybe are not fully evolved, very metal rich already, etc. where is the dust located, where is the gas located, and what are the properties of the dust in them. And these are the three things that I will be touching upon in the next 25 minutes or so. So how dusty are galaxies? First, why do we care about dust? Well, I already told you that dust is important just by the mere fact that it absorbs light and re-emits it. So if we want to really know how many young stars there are that are emitting UV emission in star-forming regions, we need to know how much is being absorbed and re-emitted. Dust in itself is also very important. It's very important as a catalyst to actually be able to form molecular hydrogen. And I think there's many people in the room here that know much more about this than I do, but it's a key ingredient for chemistry to happen on the surface of the dust grains. Then it's a coolant in the ISM, just because you have warm radiation, UV radiation, that hits the dust absorbs it, and that is a way to actually cool down your ISM and get to clumps to few tens of Kelvin where the star formation can happen along with other cooling channels. Dust also depletes metals. You have metals in the ISM, and the metals can actually stick on the dust grains and therefore lower the amount of free floating metals, so to say, that there are available. So dust in itself is really important. And on the right-hand side, you see a beautiful image of dust in a galaxy in our nearby universe. But we know that dust is relevant across cosmic time, not only because through the absorption that I saw and what the amount of obscured dust, obscured star formation in galaxies is, but also if you look at galaxies at redshift 7 and 8, ALMA has been contributing a lot in getting actually detections of dust emission, proving that dust was already present in our universe and galaxies just a few 100 million years after the Big Bang, very quickly after the first galaxy started forming. So dust is there, it's present it's really present in the ISM. So it's good to ask yourself, well, what are the properties of these dust? Now, at these redshifts, we cannot, it's hard to go into the very detailed individual grain physics of it, but we can at least start to ask questions like how much dust is there, how much dust is there compared to the metals that there are, how do you get that dust there, etc. So a very recap on dust production in a galaxy simulator's mind. So when we typically model dust formation in galaxies, there's a couple of processes that we include. The first one is just that if you have an evolved star, an AGB star, in the envelope of the AGB star, dust can form. Or if you have supernovae, condensation can happen in the supernovae ejecta, and this is where dust itself can form. Then a second mode of dust formation is the accretion of metals onto dust grains. So you have a dust grain already, there's a metal atom here, and that sticks on the dust grain and stays there, and therefore your dust mass is growing. But you can also destroy it. You can destroy dust just by sputtering. If it gets too warm, it destroys already. Dust can be used in other processes, like in star formation, and then it's called astration. You lose it in the process of star formation. Dust may also be ejected out of galaxies through outflows. There's more processes through dust. Coagulation, which is where multiple dust grains stick together and form a larger grain. So you're not gaining mass, but you're gaining size. You have shattering, where a large dust grain is being destroyed in smaller pieces. But if we're really talking about how much dust is there, then we need to understand how much dust is formed in stellar ejecta, in how much dust is formed through accretion of metals onto dust grains, and how much dust is destroyed by supernovae and sputtering in the warm ISM, or being used in star formation or blown out and destroyed in that process. So those are typically the things that are being included in these type of simulations, and that became the theory behind this has been around for a few decades already, but doing this in cosmological simulations, we really started doing about 10 years ago, a little less than 10 years ago, I'd say. So in the low redshift universe, we know relatively well how the dust to gas or gas to dust ratio of galaxies scales with metallicity. So the gas to dust ratio is literally just, you take the gas mass and you divide it by the dust mass. So if you have a high gas to dust ratio, it means you have a lot of gas compared to the dust that you have. A low gas to dust ratio means you have less gas compared to the amount of dust you have, or is very dust rich, your ISM. And what was found in the universe is that as a function of metallicity, in the local universe, as a function of metallicity, the gas to dust ratio actually decreases. So if your ISM is more metal rich, it also becomes more dust rich. And what is seen there is actually a hint of a double power law, meaning that at some point this process saturates a little bit, and the increase of dust richness with metallicity is slowing down a little bit compared to at lower metallicities. So that's known. Then if you look at models and what they predict, so this is from a paper that I wrote some years ago, what is shown here is the dust to gas ratio, which is the same thing as in the previous plot, but then flipped around. The dust to gas ratio is a function of metallicity. And on the left-hand side for redshift 0, and we're in the same ballpark as the observations. We're not spot on, but we're in the same ballpark. And then in the middle panel and the right panel, what you see is the same prediction at redshift 3 and at redshift 7. And the purple line is the prediction at that redshift, whereas the gray dashed line is the prediction at redshift 0. And there's two takeaway points from this. The first takeaway point is that in the models as well, we see that if you increase your metallicity, you become more dust rich. The second takeaway point is that, especially at the more metal rich end, there's hardly any time evolution there in this particular relation. What we find is that this relation is relatively constant with time, especially at the more massive end. That's my model. If I make a plot of this particular diagram, this is at redshift 2, and what I've done here is I've compiled all the models that made this prediction that were available about 2 years ago in the literature. And what you see is that we're all over the place. You know, my model is which one is it? The orangey line. Then you have the model by Triani, which is almost an order of magnitude below me. You see that there's a scatter of like at a fixed metallicity, there's a scatter of like almost an order of magnitude. And I'm also including here the handful of observations that are available, which is hardly anything to, and the error bars are relatively large, which is hardly anything to really constrain this. But why do we actually care about this particular plot? And the reason why to care about this is that it's actually a really cool diagram, because it doesn't only tell you about how much dust there is, it actually tells you more, also about how quickly stars are forming in your ISM. Because as it turns out, something that is very relevant here is a critical metallicity, where once you're above this metallicity, suddenly grain growth in the ISM, so metals sticking on dust grains, becomes very efficient, and it becomes the dominant mode of forming dust in galaxies. That's what essentially all the models say. They disagree a bit on at what redshift exactly this starts to kick in, or what exactly the critical metallicity is. But all of them need this as a channel for dust growth, as a relevant channel for dust growth. So there's a critical metallicity above which suddenly this becomes very efficient. Now, what happens is that I'm forming stars very quickly. Okay, so I've reached my critical metallicity, and I'm forming stars very quickly. And because I'm forming stars very quickly, I'm making the ISM more metal rich very, very quickly. And actually, the ISM is being made metal rich much more quickly than the time is needed to actually form dust grains to accretion of metals on them. So these time scales are very different. Suppose this happens. So if you have a very short time scale. What happens is that, in fact, my metallicity keeps increasing, but my dust to gas ratio, my dust richness is not really following as quickly. And therefore, I end up with galaxies that are pretty metal rich, but have a high gas to dust ratio, a low dust to gas ratio, meaning that they're not so metal rich yet, just because the time scale takes a little bit longer. A different galaxy may be forming stars, you know, has just reached that critical metallicity, is forming stars relatively slowly. So, you know, new metals are produced by star formation, but not very many. And the channel of forming dust has become, because we're above this critical metallicity, dust is formed rapidly, more rapidly than I'm actually forming new metals. Then what happens is that I'm above this critical metallicity, but the metallicity in my galaxy is not really rapidly increasing. But my dust, the amount of dust compared to the gas mass is more quickly increasing than how many new metals are forming. The takeaway point that I want you to get from here is that the scatter in this diagram doesn't only tell you something about how you're forming dust, it actually tells you something about the time scales at which you're forming dust, and the time and how these time scales compare to how quickly the galaxy itself is growing, forming, evolving. So there's more information hidden in this diagram, and I think that's also a reason why it's also very important, relevant. So, but as I said, it's not very well constrained observationally at redshifts above 0. So a trick that you can use, and I won't go into a lot of detail, but I do want to bring it to your attention, is actually absorption studies. And what you do is you take a quasar, a very bright quasar over here, and the light from that quasar travels towards the observer, towards you, and it hits some cloud of gas with dust in it. What happens is that this dust, or actually the atoms in there, they will absorb a little bit of the emission from the quasar. So you will see these small absorption features. And every individual atom will have its own little absorption features. And what you can do is you can look at, how much iron is absorbed compared to how much silicate is absorbed. And you can work out so-called depletion patterns, where you compare how much one atom is absorbed compared to another. And from these depletion patterns, making some assumption of what the original amount of iron or silicon, etc., actually is in the ISM, you can reconstruct how much dust there should be there. Because if a metal grain is sitting in the dust, then it won't absorb in the same way as if the metal atom is freely floating in the ISM. So through these absorption features, you can actually reconstruct the amount of dust in that gas of cloud that the light passed through. It's a very efficient approach because you can actually push this to very low metallicities, significantly less than 10% solar. So what we did, or actually what Celine Peru did together with Hauk in a review paper, is that they compiled all of this together. And then in a paper that I wrote with Celine Peru, we just made this plot of dust to gas ratio versus metallicity. And then you can do this all the way up to redshift 5. And then what you see is a clear decreasing trend again. Lower metallicity galaxies have lower dust to gas ratios, lower relative amount of dust. But also quite relevant, what we did, we made a fit at redshift 2, 3 in the middle, and that fit is then being shown in the other panels. And what you see is that there's no real evolution in this plot again, in this trend again, suggesting that the relation between dust to gas ratio and metallicity is constant with time. In the paper itself, we did a whole exercise of comparing this to all the models that are on the market and what we can learn, what aspects of dust grain physics work, what aspects of dust grain physics included in simulation doesn't work, which quickly becomes a very technical story. So if you want to know more, ask me over coffee afterwards. But okay. But one of the downsides of the approach, so the upside is that you can actually get many galaxies down to low metallicities. One of the downsides is that what you're doing is you're taking a single sight line through an intervening gas, cloud of gas with dust. And this may be the center of your galaxy, it may be somewhere in the outskirts of a galaxy, and it's just one sight line through that particular object. So you don't know what you have is just many sight lines which together give you a statistical information, but you don't really know what an entire individual galaxy is doing, or even later on starting to resolve that galaxy. So to do that, you need to go to emission, which is something that we did together with Irene. So what I'm showing you here is 3 galaxies from a ALMA program that Irene led a couple of years ago, where we aimed to get dust continuum measurements of 27 galaxies, normal star-forming galaxies. So not the most massive ones, not the most actively star-forming ones, no, normal ones. And ones with metallicities less than solar. So that was still really evolving. And a subset of these galaxies also have CO information, and CO provides us a gas mass. So putting that together, you can actually start to do this exercise of metallicity versus dust to gas ratio. And what you get then is the following. So on the y-axis, you see the dust to gas ratio of galaxies. On the x-axis, you see metallicity. And what you should focus on are the blue dots over here. Now, I have to be honest, it's just a handful of galaxies. It's for 10 galaxies we had coverage in both dust emission and gas, but not all of them were actually detected in both. So there's only 5 in which we really have a detection in both securely. But the takeaway point here is that these are the first few galaxies, together with a handful of more galaxies from the literature, for which we can do this exercise at cosmic noon in emission, where we can say, well, this is the dust to gas ratio of galaxies as a function of metallicity. And then the line, the blue dashed line, is a fit to it, and the gray area is redshift 0. And again, the takeaway point is that we're definitely in the same ballpark. We're not an order of magnitude higher, we're not an order of magnitude lower. But I also need to be honest, we're not really probing the low metallicity end very well, so it's hard to say how the trend evolves with metallicity. We don't know. All that we know right now for sure is that at least these dust to gas ratios are comparable, which is actually already quite useful to know, because it has become popular to, if you know the dust mass, you know the gas mass. That exercise has become quite popular. This suggests that, at least with the data that we have today, it suggests that the relations that we used to do this exercise based on redshift 0 data hold at least at redshift 2. But it's just the beginning. So to really do this properly, what you need is a large sample for which you have gas measurements, dust measurements, for which you have metallicity measurements, etc. And that's where our large program comes in that was recently accepted. So what we're trying to do is exactly that. So we'll be, oh yeah, here it is. So what we're trying to do is exactly that. This is a plot that I took from the proposal, but the takeaway point is that with this large program, we've gotten about 130, 140 hours of ALMA time to do this exercise for these normal galaxies, to actually really integrate much longer than we did before, to populate, if you look at the previous plot, to populate that area in the orange circle where there's no information yet, so that we can start to really compare if the slope of these trends is similar to redshift 0, if it is in agreement with what we saw in the absorption studies, and then hopefully to provide constraints for theoretical models so that we can bring the order of magnitude differences down to significantly less. And just to illustrate this in the tip of the iceberg type of exercise, so on the bottom you see the plot that I showed earlier, where I said, well, we've only really covered the upper right part. We are now starting to cover also the lower regime. We're not talking about thousands of galaxies. It's relatively small samples, but it is the beginning to really push further than what has been done observationally with ALMA before. So where is the dust located? Resolved dust emission. So what I'm showing you here is a plot from a paper by Melanie Kaasinen, and Melanie resolved a couple of cosmic noon galaxies in their dust emission. And as I said earlier as well, when I say resolved, what you see is that it's a handful of beam elements. It's not beautiful spiral structures. There are some examples of that as well, of the most massive galaxies out there, but we're thinking about normal galaxies. We're only just starting to do this with ALMA. At the same time, as you may know, ALMA has baselines going up to 16 kilometers, and the reason it has that is because it allows you to have very, very fine angular resolution observations. So theoretically speaking, we can do much better, and we hope to do much better. And luckily, there's a large program recently accepted, Condor, which will actually start to do much better for large samples for our standards of like 10 galaxies. But, great, this is going up. So what can we learn so far, and what do we expect? Well, one of the interesting results that is out there in the literature based on the data that is so far is the following. What you see on the y-axis is the size of the dust size of galaxies, the radius that contains half the dust emission. And on the x-axis, you see the stellar light radius, so the radius that contains half the 1.6 micron emission in these galaxies. And one of the takeaway points is that almost all these galaxies lie below the 1-to-1 curve, meaning that almost all these galaxies have compact dust distributions compared to where the stellar light is. And the CO is the same. And it is thought that, what this actually shows you is that there's a lot of active star formation going on in the center, and that this is where you're building up a dense central component. So can we repeat this, as we're waiting for these high resolution observations to come in, and with the data that we have, can we say something about this from simulations? So what I'm showing you here is a work from some years ago where we took thousands of galaxies from the Illustris TNG simulation. The Illustris TNG simulation is one of these bigger cosmological simulations where for a large volume individual galaxies are formed, how many, with all the baryonic physics included. So star formation, supernova feedback, the mergers, accretion of matter, outflows, name it, you name it. So we took thousands of normal star-forming galaxies from this simulation, and then we coupled that to the radiative transfer code SCIRT. If you want to know details, I can tell you afterwards. I'd be happy to talk about that. And then what we did was just a simple exercise of what we saw before, measuring the half-light radius. Like if I do the radiative transfer calculation such that I get a beautiful map of this galaxies, of its dust continuum emission, how large is it? And how large is it compared to other things? So what you see, these are galaxies at redshift 1, 2, 3, 4, 5, and then the size at 815 micron, which is the typical wavelength at which these type of dust studies are being done. There's two takeaway points. The first takeaway point is that there's no strong trend of the radius at 850 micron with stellar mass. It's not like the more massive galaxies are suddenly much larger in the dust continuum size. And you see a redshift trend, right? At redshift 1, galaxies are larger than at redshift 5. The universe was older, the galaxies on average all grew. So, but now the interesting thing. Before we go into how dust compares to other things, what does dust continuum emission in itself actually trace? Does it really trace dust? So what I'm plotting here is on the y-axis the ratio between the size of dust, so the radius that contains half the dust emission, the size of dust emission, by the radius that contains half the dust mass. And if that ratio is 1, it means that the emission from dust is coming from the same, on average, regions as where the dust itself is located. But what you see is that always this ratio is less than 1, it's about 0.7 or so, meaning that where the dust shines is not necessarily the same distribution as where all the dust is located. Actually, it's more compact. So what does dust trace? So what I'm plotting here on the right-hand side is the same. So the radius that contains half the dust emission divided by the radius that contains half the star formation in the galaxy, which is fairly close to 1, not exactly. So what it tells you is that what this dust emission really is tracing is just where the star formation is. Which in a way makes sense because you need young stars that produce UV emission that is being absorbed by dust, and that dust will then shine brightly in the dust continuum wavelengths. If you have dust somewhere over there and there's not a lot of UV emission, then you won't really see it either. So dust continuum is systematically more compact than the dust mass, and it closely follows star formation. So we said earlier that the dust was compact, right? The dust was compact compared to the star. So what's shown here is a similar type of plot. On the top hand, where I take the ratio between the radius containing half the dust emission and the radius containing half the stellar mass, so where the stars are located. And earlier on, I said that dust was compact compared to the stellar light. But what we see here is that this radius is usually 1 or even higher, meaning that the location where the dust emission is coming from is even more extended than where the stellar mass is located, which is not the same as what we saw earlier. But if you listen very carefully, I very specifically always said either stellar emission or stellar mass. Because if I now make the same plot as the observers do, where I take not the radius containing half the stellar mass, but the radius containing half the stellar light at 1.6 micron, which was one of the Hubble filters, then suddenly all these lines are below 1, meaning that the dust emission is very compact. Okay, so dust emission is compact compared to the stellar emission at that particular wavelength, but it's not compact to where the stellar mass is located. So why is that? So what I'm showing you here is 1.6 micron emission, the radius of 1.6 micron emission, divided by the radius of the stellar mass. And this is close to 1, not exactly, but it's relatively close to 1. I'm showing you that the stellar light traces the stellar mass. But this is a run where I completely ignored dust. Dust does not exist. There's no dust absorption. This is a run where I did include dust. There is dust absorption. And what you see is that suddenly this ratio changes quite a lot. And what happens is the following. I have a beautiful stellar light profile. And there's a lot of dust in the center. And therefore, my light profile, this emission here is absorbed. Therefore, my light profile does that. And what I'm doing here is then I'm taking the half light radius, or I'm fitting some exponential to it. And as you can see, the sizes of that half light radius or that exponential will actually change quite a bit. This is exactly what's happening. And you see a redshift trend here, right? At redshift 5, it's much more prominent than at redshift 1. And the reason is just that at a wavelength of 1.6 micron, 5 minutes? Okay, of 1.6 micron, I'm tracing much bluer emission at redshift 5, which is being absorbed much more than I am at redshift 1. So I completely mistimed this, so I'm skip over James Webb, because who cares about James Webb? And I'll go to where the molecular gas is located. So I'm showing you here some results from these three people, Ivana, who's sitting here in the room, and Anirudh, who was a master student with me, and Melanie, who's a fellow at ESO. And so I've shown you these maps before, right, of where the molecular gas is located. And this is CO1 emission, this is CO3 emission. But the question to ask is really, how extended is this CO emission actually? How large are these galaxies? And what does it tell us about where the molecular gas is? And how well does CO actually trace molecular gas? So a way to approach this that we did, or actually that Ivana did here, who will join CAB in a few days officially from now, in case you don't know her, is that we took galaxies that were detected with ALMA, nicely detected, and we stacked them. And the reason to stack them is that by stacking them, we were hoping that faint emission at the outskirts was going to show up. So that's exactly what she did. She took a sample of galaxies that were available in the archive. And if you stack these 26 galaxies, what you see is this. Which is a beautiful bright blob in the center of your image. So it doesn't show you a beautiful distribution. That's partially on purpose because it's not like these observations have very high angular resolution. But what you can do is you can make radial profiles. So what's shown here on the right-hand side is, first of all, it's good to focus on the yellow line, which is the PSF, so which is kind of the resolution of your data. And in the stack, the blue line here, the purple-blue emission that you see is the emission that we're actually measuring. And the takeaway is that these two don't fall on top of each other. The blue is more extended than the PSF. So we are resolving some emission beyond the PSF of the data. And then if you look carefully, then you'll see that what we're doing is we're resolving emission all the way up to about a little bit more than 2 arc seconds or so. So the dashed horizontal line is the noise limit of the data in this stack. And what this means is that we're seeing emission going out to scales of about 16, 17, 18 kiloparsecs or so, which is actually pretty large. Now, what's being measured here is actually the convolution of the actual emission and the PSF. So if you correct for that, what we're seeing is we're seeing CO emission out to sizes of about 12 arc seconds or so, which is much larger than typically found than typical sizes that we find for stellar emission in the literature. So the question is, how do you get that emission there? So that's also something that Ivana looked in. She stacked the spectrum, and the idea was that maybe there's outflows bringing all the gas out there. And if there would be outflows, what you would expect in the spectrum was really a nice Gaussian component and a broad wing under it of all that high velocity gas going out there. We fitted the spectrum with 1 Gaussian or 2 Gaussians just to see if you get a significantly better fit if you do multiple Gaussian fitting, and the answer was no. So we don't really see strong evidence for outflows bringing the gas there. It's too early to say what exactly is the gas at these larger radii, but it's definitely there, and we should try to understand better how it got there and how much is there. So that's future work. I'm just going to show you assimilation efforts that we're doing at the same time. So we're also approaching this from the simulation angle, where we take the cosmological simulation, do full radiative transfer to make predictions of how much CO there is in these galaxies. And what is plotted here is radius on the x-axis, and on the y-axis the surface brightness of different CO transitions. And here as well, what you see is that this emission goes out. I'll add the scales. This emission goes out easily towards radii of 10 kiloparsec or so, or even more. But the second takeaway point is, if you look here carefully, there's the white line. The white line is where the molecular hydrogen is located. And the CO does that. And the molecular hydrogen does that, right? So it also means that at some point at larger radii, the CO is not tracing the molecular hydrogen so carefully anymore, which is complicated. We did this exercise for many galaxies at different redshift, at different stellar masses. But to really focus just on the alpha CO profile, so alpha CO tells you how you translate CO emission to molecular hydrogen mass. Here you clearly see that when you go towards larger, for you here, larger radii, this alpha CO number quickly rises up, meaning that CO is a much less good tracer of molecular hydrogen than if it were to be very low. Or to be more quantitative about this, what we see first of all is that alpha CO remains relatively lower for large stellar galaxies with large stellar masses or high metallicities, which is expected because we know there's a metallicity trend. We also see that the alpha CO can go from typical values of 3, for those to know, to 100, and one at the outskirts. And once it's 100, it means that it's really hard to actually detect that CO emission and translate that to a molecular hydrogen mass. So that's posing some significant challenges for us as a community. And why is that? Why does that happen? So in the simulations, you can look into that. And really the driving factor is just that the chemistry of that is happening means that the CO abundance, how much CO you have to begin with, is significantly lower. There's also secondary effects that have to do with how warm the gas is or the velocity dispersion of the gas. But the main driver is just that the chemistry that sets how much CO molecules you have to begin with tells you that you have not that much CO in the outer regions of the galaxies. Now, this is just model predictions, but ALMA will be able to actually probe these scales. And we very much look forward to seeing if we, first of all, seeing if we find similar profiles, but also we need to think about how to translate that to actual baryonic properties like molecular hydrogen masses and how that fits together with where the dust is located, where the stars are forming. So, as a takeaway messages, what we find is we find so far no evolution in the dust to gas ratio of galaxies with cosmic, as a function of metallicity with cosmic time. At the same time, it's too early to say this conclusively. It's hinting with the data that we have in that direction. The ACE large program that we have will be a significant step forward in going towards more conclusive answers. Second, what we find is that dust absorbs stellar light, that we knew. It means dust can change the profile that you have, the stellar light profile of galaxies, but it can change it quite significantly. So really going towards the longest wavelength where dust absorption is less prominent is very important if you want to know where your stars are located. And also then to really do the comparisons of where the stars is, where the gas is, where the dust is, etc. And lastly, we see that CO emission extends to scales above 10 kiloparsecs. So these galaxies have sizes going out to more than 10 kiloparsecs, but this is just the beginning and we need to go deeper. And as really the final takeaway, what I want to say is that, ALMA has been, I work for ALMA, so I have to say this, ALMA has been absolutely a fantastic instrument. And the last decade has shown us a lot improvements in our understanding of what gas and dust in galaxies are doing. We've just celebrated a decade of ALMA a year ago, and now is the time to go beyond the tip of the iceberg, to really go towards the much challenging things where we're really resolving galaxies, which is hard, which takes time, but we have to do it. Where we go to the low mass galaxies, which is hard, but it takes time. And to really build a sense of what the bulk of the galaxies out there in the universe that are responsible for all the beautiful stars you see in the night sky, how they were formed. And with that, I thank you.
Thank you so much, Gergö. I hope it's right. Couple questions.
Hi, that was a really interesting talk. I have a question regarding your first diagram, that one on the top, and it's how, I mean, all these points, they go down like almost 8.5 in oxygen, and those are redshift 2.3. If you look at them I'm wondering how significant are these galaxies of the average galaxies you find in the universe at that redshift? Or in other words, are these galaxies a bit too massive for being the main sequence? If you look at the Matteo-Dickinson plot and you look at the expected metallicity, average metallicity of the universe at that redshift is about a factor of 10 below what you find there. So I'm wondering whether you're probing there's the normal galaxies that were forming, or just, again, the tip of the iceberg, or the most luminous, more massive galaxies that are producing such a big enrichment or high enrichment in oxygen.
Yeah, I think there's different ways of looking at this. So if you look at, if you take a stellar mass function, which it tells you how many galaxies with a certain stellar mass there are in a universe as a function of the stellar mass, it has a knee, right, which is called m star. And the knee is the location, what will be the most of the mass in the universe is at that knee location at a given redshift. So with the metallicities that we're probing here, which in the survey will go down to 8.2 or so, we're definitely probing galaxies at that knee and a little bit below it. If you look at by number, most of the galaxies by number are the low mass galaxies that have metallicities, maybe even significantly less. That's definitely true. But with this survey, what we really can do now is, not only probe, again, if you think about the stellar mass function, the very massive objects out there of which are not few, we go towards the flat end of a mass function, where we know that where the most of the mass at a given redshift is actually located.
So what would be the typical?
That's about 10 to the 10 solar masses. In the survey, we are between 10 to the 9.5 and 10 to the 10.5. So we cover that range around it. So, but I have to admit, I mean, when I say low metallicity, I mean like half solar down to 10% solar, maybe, which is not the same as what someone who studies stars in the Milky Way would call low metallicity. So there's a difference in definition there.
I had a second question. Yeah, when you say metallicity, you rely on oxygen, and we know that there's maybe it could be a decoupling of the iron enrichment and the alpha elements like oxygen, and this has to be very important for the formation of dust. So I wonder whether that is taken into account in this kind of galaxies, that if they're having a higher star formation rate, they will quickly enrich the alpha elements and not so much the iron. What is the impact in the dust formation there?
You're putting me very far outside of my comfort zone here. I think so far what's being done here is, when we measure these metallicities, is that we can measure a number of rest optical ionization lines, and from that work out what the oxygen to hydrogen abundance is. If your spectral quality is high enough, and I think that definitely NIRSpec has a lot of promise there. If your spectral quality is high enough, then you're able to go into much more details, and not only looking what your oxygen abundance is, but also other types of abundances. Then how that translates to the type of the dominant process of dust formation and how that depletes various types of atoms, I cannot do that math at the moment here right now. But I don't think that that's a level of detail that this field has really even gone into. The groups that really focus on absorption have gone more into this, because they're probing all these different depletion patterns, so had the potential or to look more into this. But I would not be in a position right now to tell you, and this is what they find, because I don't know for sure.
Thank you. Thanks for the nice talk. I was interested in your last part of your talk regarding the regions in the galaxy that you're missing, no, because you are using CO as a tracer of the gas mass. Then I was wondering how much mass you're missing according to your simulations, whether that is a significant fraction of the mass of the galaxy, and what tracer do you plan to use in the future to reach that CO dark gas?
Yeah. The mass fraction that is missing, it's not like we're talking about 90% of the mass that is missing. In the end, most of the molecular hydrogen mass is sitting in the center of the galaxies where we're quite sensitive. What is showing here is just the surface brightness. I've not shown you cumulative mass fluttering. So the fractions that we're missing is more at the level of a couple of percent out there. But in the end, it becomes relevant when you, maybe up to 10% or so, but it becomes relevant, maybe not the extreme case where your alpha CO is 100, but there is already at 5 kiloparsecs or so, your alpha CO is not the typical value that we would use for normal galaxies of 3.5, 4, but it starts to become 5 and 6. And then if you're then comparing how much molecular mass there is to the star formation rate, then if you don't correctly account for it, your star formation efficiency suddenly seems weird or is different from what it actually is. And for me, the takeaway from this is that even within one massive galaxy, if you think about, I know that it's metal rich and this is the alpha CO, once you go towards the outskirts, just because the metallicities are different, even in these massive galaxies, there's not one number, which is logical, but we should show it at some point. Right? The second part of your question, in the high redshift community, I think the most frequently used alternatives are either atomic carbon. There is a metallicity dependence as well, but it's less strong than it is for CO. CO is brighter in itself than atomic carbon, as in emission. But there will be some metallicity, which, the chemistry of CO versus the excitation of atomic carbon, where atomic carbon starts to win. Especially in environments with lots of cosmic rays, CO is very quickly destroyed. So their atomic carbon is a plus. C2 is also considered quite a lot, ionized carbon, with the assumption that it's ionized carbon coming from your photodissociation region linked to ongoing star-forming regions. But C2 can also be ionized just in warm ionized gas, where it has nothing to do with molecular gas, really. So that's also something that you need to take into account there. So as always, there's not one best answer there. There's just several approaches, and we need to work hard in properly understanding and calibrating these. Then, you have hydrogenated deuterium, I don't know, other types of things that in theory you could use, but at these redshifts, it's too faint. Yeah. It's being tried, but you can only do it for the most massive bright objects out there.
So we have time for one last question. Anyone? Maybe on Zoom? Miguel? No one?
There's no questions on Zoom.
Okay, so thank you again. Thank you very much and for your talk. And we go to the cantina to continue.
Good.